Hello, my name is Brian Crafton, and I will be presenting our work titled Improving Compute Memory ECC Reliability with Successive Correction. My co-authors are Zishan Wan, Samuel Spitelnik, Jong-Hyuk Yoon, Wei Wu, Carlos Tortunaga, Vivek Day, and Arijit Ray Chowdhury. And we are from the Georgia Institute of Technology, the Daegu Institute of Science and Technology, and Intel Labs.
First, I will introduce compute memory. Next, I will characterize device challenges faced by compute memory using real data from our test chips. Then I will review some ECC techniques from prior work. And then I will detail our technique, successive correction, and show our results.
The easiest way to define compute memory is to compare it with a typical memory array. Here I'm giving a small example of the two. Starting with the typical memory array, we have a 4x4 bit cell array with some peripheral circuits. So the open circuit here denotes a logical 0, and the short circuit here denotes a logical 1. And we have word line drivers to read each word line or row, and we have sense amplifiers to read the 1 or 0 from the corresponding bit line or column. And at a high level, the only change we make to enable compute memory is swapping these 1-bit sense amplifiers for an analog to digital converter. This allows us to sense more than 1 bit of information on the bit line, so let's see how this works. Here I am showing the operation of these arrays as animations. So in the typical memory array, we can only read one word line at a time and we sense 0 or 1. But in the compute memory case, I can enable several word lines at the same time and sense the summation of the result. So if we have a single 1 enabled, we get 1. If we have 2 enabled, we get 2. And if we have 3 ones or short circuits, then we get 3. And we can activate arbitrary word lines at the same time. So what are the pros and cons of doing this? Well, the main advantage is we get higher memory bandwidth. If we activate n rows, then we get n times bandwidth. Next, we reduce communication costs, so rather than sending n bits, we send log n bits. And lastly, we get free compute, meaning that we get the summation along the bit line for free since it's in the analog domain. Of course, this operation only works for applications or kernels that want to sum the values together, like matrix multiplication. What are the challenges? So by increasing the amount of information along a bit line, we increase noise, IR drop, and we decrease our voltage headroom. And all of these contribute to unreliable operation. So the trade-off here is really performance for reliability.
Compute memory has been applied to several memory technologies, SRAM, DRAM, and emerging non-volatile memories, just to name a few. For this work, we'll apply our techniques to RAM for a couple of reasons. First, we have fabricated several recent test chips using RAM, and so we have access to a lot of high quality and accurate data. And second, RAM is an exciting new memory with high density and non-volatile storage. Here is a die shot of the test chip recently presented at ISSCC 2022. The test chip is fabricated in TSMC's 40nm RAM and CMOS process. It is 25 millimeters squared and has 2.25 megabytes of on-chip RAM. And it also has an embedded Cortex M3 on chip. So using this test chip, we can characterize compute memory errors. First, we'll look at some histograms of measurements from reading RAM in the low resistance state and the high resistance state. And going forward, I will use LRS and HRS as abbreviations for low resistance and high resistance state. So for reading this as a binary memory, there's no problem. The bit error rate is low and we can easily distinguish between the LRS and the HRS, namely the blue and the orange groups of samples above. But what happens when we turn on multiple word lines to perform compute memory? To test this, I just wrote arbitrary patterns to RAM arrays and then measured the bit line voltage that feeds into the ADC. The figure on the bottom left illustrates this test. The main idea is that we want to collect a large number of samples with various numbers of LRS and HRS devices to identify errors. The result of this is shown on the right as a histogram. It's clear that reading multiple word lines at the same time generates errors since many of these distributions are overlapping from each other. So how do we evaluate this error? For typical memory systems, we use bit error rate, which can be used here, but it is a bit more complicated than that since it's not just 0 and 1. So we can utilize a confusion matrix to properly capture this, which is shown on the right. The confusion matrix shows the percentage of time the expected ADC output, or the number of ones in the bit line, was interpreted as the actual ADC code. Obviously, we want the expected to match the actual, So the percentages along the diagonal represent correct operation, and all others represent errors. To create this matrix, we loop through the set of all samples and increment the bin that corresponds to the sampled results. Then we normalize the matrix. So we can see that we achieved 100% accuracy when there are only a few ones on the bit line, and then this falls off as we increase the number of ones we read. So what causes these errors? Well, there are a number of sources, but for this work I will focus on just device variation. Device variation is the standard deviation from the mean in the LRS and HRS. We saw before how this variation is negligible when reading only a single cell, but this becomes problematic when reading several cells at the same time. To get an idea of what device variation we can expect, we ran an experiment. So for 3 different programming voltages, we set and reset 8,000 cells and measured their resistances. I have plotted these experiments as cumulative distribution functions. From this experiment, we can observe a few things. The device variation is a function of the programming voltage. So we can see that the black curve is tighter than the blue and green curves because a higher voltage is used. And we can push this device variation quite low, close to 4% in the case of the LRS mean resistance. The classic way to overcome errors in memory is to apply error correction codes, or ECC. One major challenge in the implementation of ECC for compute memory is that classic SecDed does not work for compute memory. However, several recent works have proposed new codes that work well. Although each of these codes has their own merits and use case, I would like to highlight the first 2 works in this table as the best overall choices. Both implementations offer single error correction, double error detection at only 1 additional parity bit compared to traditional SecDed. Furthermore, their CMOS implementations of their decoders are relatively low overhead as well. And although each of these techniques is unique, they all have similar physical implementations, where we add 2 additional blocks to a standard memory array. And to illustrate these ideas, I will walk through the implementation of SimSecDed. However, the same really applies to all the other codes. To implement ECC, we can start with the standard 256 by 256 memory array based on the arrays in our test chip, where we can read up to 8 word lines at a time using a 3-bit flash ADC. To add ECC, we need to make 2 modifications to our array. First, just like SecDed, we allocate a fraction of our bit cells to serve as check bits. We use a 32/8 SecDed code, so for every 32 data bits, we have 8 check bits. And second, we require a decoder. So upon reading the array, the decoder takes the digital outputs from the ADC and can detect and correct errors. So let's see how these additions work. In this example, I will break down SimSecDed into the 3 main components: encoding, detection, localization, and lastly, correction. The differences from regular SecDed will be highlighted in gold. The 4-bit data will be used as shown here, and to illustrate compute memory, we will read 4 consecutive rows. And the ADC results are shown below the array. The first step is encoding check bits for performing ECC. The parity bits we encode are the exact same as regular SecDed. The new encoding step is these 2 sign bits that serve as a checksum for computing the sign. This is important for compute memory because we need to know if the error was a plus or a minus 1. This is not needed in typical DRAM because if an error occurs, you just flip the bit. So if an error occurs during compute memory and we detect it, we can compare the compute memory result with this 2-bit checksum to see if the error was positive or negative. The next step is detection and localization. So as an example, let us assume that a single error occurs at the 3rd data bit. So instead of 3, we got 2. To detect and localize this error, we can use the exact same logic as regular SecDed. All we have to do is look at the least significant bit. And from here, we can perform localization the same exact way as SecDed by translating the syndrome as the bit address. And now that we have localized the error, the last step is correction. This requires us to compute the sign of the error. To do this, we can compare our expected checksum versus the actual checksum. So if we do this math out, we'll get 0 for the actual checksum and 1 for the expected checksum. And so a 0 minus 1 implies a negative 1 error. So we would then go add 1 to the 3rd ADC to complete correction. So SimSecDed and the other ECCs can offer good error correction at a small penalty compared to traditional ECC. But is this good enough? Well, if we assume the bit error rate of compute memory is on the order of 10 to the minus 3, then even with SecDed, our bit error rate should be 10 to the minus 6. In comparison, SRAM has a bit error rate around 10 to the minus 15. And while some applications, like deep neural networks, are quite error tolerant, we want to be able to enable compute memory for a broader class of applications, for which 10 to the minus 5 is not good enough. And so if we could enable double error correction or triple error correction, as opposed to single error correction, we could get to 10 to the minus 9 or even 10 to the minus 12, which would be a lot more compelling. To accomplish this, we propose successive correction. Successive correction makes use of two key ideas. First, reading less word lines yields less errors. And second, we can detect two errors with SecDet because we have single error correction, double error detection. And so we can use this detection capability to actually perform correction. But let's see an example. In this example, we read 4 word lines and the result is measured by the ADCs at the bottom of the array. But let's say, for example, we get an error and it occurs in the second bit from the right. So instead of a 2, we get a 1. Upon detecting this error, we can break down the 4 word lines into 2 sets of 2 word lines. And if we get another error, break down the 2 word lines into 2 sets of 1 word lines. And this allows us to actually perform double error correction using our SecDed code. But we can actually do better than double error correction. A lesser known idea is that the SecDed code we have been using can actually detect 3 errors. A SecDed code is a Hamming distance of 4, which essentially means we can do single error correction, double error detection, or just triple error detection. And normally triple error detection has no practical utility, but here it is actually very useful. So following the same logic as before, we can enable triple error correction using triple error detection.
Now that we have made it through the algorithm, we can see some results. So for the experiments in this paper, I simulated ResNet 18 on ImageNet and swept various device-level parameters such as device variation and stuck ad fall rate. Then I gathered bit error rate, performance, and application accuracy. To compare performance, I computed the normalized performance of each scheme. By normalized, I mean I divided the performance of each ECC scheme by its respective overhead. So for example, for no ECC, this would have ideal performance, while SecDed will have about a 75% performance based on its area overhead. The first result I am showing is bit error rate versus LRS variation. We sweep LRS variation from 2 to 10%, which is roughly what we expect from RM based on our measurements and results in the literature. As expected, we find that triple error correction does better than double error correction, SecDed, and ECC. Next, I am showing the performance for this simulation in the top figure. We see that performance of double error correction and triple error correction starts out equal to SecDed because they have the same overhead, but then falls off as we increase LRS variation. This is because we spend more time rereading word lines. And this indicates that for some cases it can be disadvantageous to use successive correction. However, at 3.5% device variation, we see a 16,000 times improvement in bit error rate compared to ECC and a 636 times improvement when compared to SecDed with basically the same performance. The next result answers the following question. Can we improve performance by using ECC? To test this, we run the following simulations. In simulation 1, we enable 32 word lines without ECC. In simulation 2, we enable 32 word lines with triple error correction. And in simulation 3, we enable 8 word lines without ECC. From these simulations, we observe that enabling 32 word lines with triple error correction yields better performance and better bit error rate than running only 8 word lines without any ECC. At 3.5% device variation, we see a 2.32x improvement in performance and a 200x improvement in bit error rate. And this indicates that even for designs with low bit error rate, it is possible to push performance by adding ECC. So in conclusion, compute memory reads multiple states at once, which generates more noise and lower voltage headroom, and this results in an inherently higher bit error rate. In this work, we presented a new technique to boost protection capability of existing ECC schemes. We realized that using detection, we can actually perform correction by rereading smaller subsets of word lines when errors occur. For the devices we characterized, our ECC scheme yields a 16,000 times improvement in bit error rate over not using ECC, and a 636 times improvement over the state of the art.